So now we have discussed the data flow analysis framework in a lot of detail and also talked about its various properties. Now let's look at some examples of DFA-based transformations, some of which we are already familiar with. So for example, we have looked at constant propagation, copy propagation, dead code elimination, which is based on the liveness DFA analysis, which is actually a backward analysis. The other two that I mentioned, copy propagation and constant propagation, are forward data flow analysis. Common subexpression elimination. And we're also going to discuss loop invariant code motion and partial redundancy elimination in the next few lecture modules. So here's an example. Let's say I have a program which says for I equals 0 to n, I plus plus, ai equals m plus n, an minus 1 plus equals ai plus 1. Now in this particular program, there are a couple of things that are loop invariant, which means they don't really change across different iterations of the same loop. What are those computations? Well, one of them is m plus n. Notice that this loop is not actually changing m, neither it's changing m nor it's changing n. And so m plus n is actually a constant across the iterations of the loop. In other words, m plus n is loop invariant. Also notice that this particular computation here, which is the address of element I in array A, is not loop invariant because it changes with every iteration, because every iteration has a different value of I, and so AI would be different value for the address of AI would be different value in every iteration. Similarly, AI plus 1, both the address and the value of AI plus 1 are going to be different in every iteration. But let's look at this one, an minus 1. So n is loop invariant, and so the address of an minus 1 is also loop invariant. And so there are two computations in this particular loop which are invariant across iterations of the loop. And so it is possible to implement loop invariant code motion. So that's the name of this particular transformation, where you move the computation which is loop invariant outside the loop, all right, typically before the loop. So for example, here you do m plus n in the beginning of the loop, say t1 equals m plus n, and similarly you do t2 equals the address of an minus 1. So in the C syntax, that's using the ampersand operator. So t2 is just the address of an minus 1 computed once in the beginning of the starting of the loop. Now this is likely to be a beneficial optimization if the loop is going to execute at least a few number of times, potentially a large number of times, maybe tens of times or hundreds of times or even thousands or millions of times. In which case this is a very useful optimization, because without this optimization we would have, using this optimization we are saving potentially millions of operations if the loop had million iterations. Alright, so now the loop just becomes ai equals t1 and star t2 plus equals ai plus 1. So instead of m plus 1, I just replace it with t1, and instead of an minus 1, which involves arithmetic of adding n minus 1 to a, all that has been done a priori into t2, and I just need to dereference t2 and then add ai plus 1 to it. So these are examples of loop invariant code motion transformations, and we want to know how we are going to implement such transformations. First of all, once again, I want to point out that these are very consequential transformations because the loop may execute a large number of times. I also want to point out that it is not necessary that this transformation actually reduces your program time, because if, for example, it was true that the loop was n was 0, for example, in this example. So if n was 0, this loop would have never executed. And if this loop would have never executed, I would have never had to compute m plus n, or I would have never had to compute the address of an minus 1. And this transformation is actually always going to, it's going to cause that computation to always happen. So in that rare scenario where n is going to be 0, we may end up doing more work in the optimized or in the transformed program than in the original program. But typically we expect that if the programmer has written a loop, it's likely to execute at least a few number of times, typically large number of times. And so a compiler can make this approximation. Once again, compiler is making a trade-off here between the probability that the transformation is actually going to cause a slowdown is small, and the probability that the transformation is going to cause a speed up is large, and the associated speed up itself is also large, and the associated slowdown is also small, because if the loop was not going to execute even once, then all we are doing is adding 2 extra computations on that path. On the other hand, if the loop was going to execute, at least let's say 100 times, then we have saved 200 computations. So, what the compiler needs to make these trade-offs when it is doing these transformations. And typically, loop invariant code motion is considered a very profitable transformation, as in this example. All right. So we are going to talk about one transformation which is called, we're going to talk about a category of transformations which is called partial redundancy elimination, and we are also going to call it lazy code motion in subsequent modules. So the good thing about partial redundancy elimination, I'm going to describe what it is in the next few slides, is that it subsumes a few different transformations. For example, it subsumes common sub-expression eliminations. We have already learned about common sub-expression elimination earlier. And partial redundancy elimination subsumes CSE. Why? What do I mean? I mean that if you implement partial redundancy elimination, all common sub-expressions would automatically get eliminated in the same algorithm. Similarly, partial redundancy elimination subsumes loop invariant code motion. So that seems pretty powerful. A single transformation can subsume both loop invariant code motion and common sub-expression elimination, and it gives you a few extra capabilities. All right, so it is a very powerful transformation. It is also based on data flow analysis. It is one of the very interesting ones because it involves multiple data flow analyses to be fit together, and we're going to use this as a case study and study it in more detail in the next few lecture modules. I should also mention that partial redundancy elimination is a practical transformation that is typically implemented in all modern optimizing compilers. All right. So what is partial redundancy elimination? And to understand that, let's look at this particular example. So in this example, I'm computing B plus C on one branch, and I'm updating B on the other branch. And then on the meet point, again, I'm computing B plus C. Now, B plus C is partially redundant. The computation B plus C is partially redundant. Why do I say it's partially redundant? Because it's redundant only on some of the program path. So it's only redundant on this program path. It is not redundant on this program path. In other words, on this program path, I don't need to do it again. I could have used common sub-expression elimination to eliminate the second one and kind of reuse the previously computed value. But on the other path, I still need to compute it. And so this computation is only partially redundant. This is in contrast with common sub-expression elimination, where we eliminate an expression only if it is totally redundant. So here, because in common sub-expression elimination, recall that the meet operator is intersection. And so if I run the common sub-expression elimination algorithm on this particular example, I won't be able to eliminate B plus C on any of the paths. All right. But partial redundancy elimination is a more sophisticated idea. And in this, we are going to say, okay, so for example, I may want to transform it on the right side. And so the right program here is the optimized transform program, which does not have partial redundancy. So how does it work? Well, on the left hand side, we just basically have the same computation, just that we store it in a temporary variable t, and then just do a equals t. Recall that creating these extra copies is not a problem as long as we're going to do copy propagation later on. Hopefully that's going to solve these problems for us. And on the other branch, I basically, after I do b equals 7, I recompute b plus c only on this particular branch. And then at the meet point, I just do d equals t. So what have I done? I have eliminated the partial redundancy. If you look at it, on both the paths, b plus c is not redundant. Right? So b plus c is not being recomputed redundantly on any of the paths. And that's why it's called elimination of partial redundancy. In the original program, b plus c was redundant on some of the paths. That means it was partially redundant. In the transform programs, b plus c is not redundant on any of the paths. So the partial redundancy has been eliminated. On this particular path, b plus c is only computed once. And on the other path also, b plus c is only computed once. Okay, so that's what partial redundancy elimination means. And so, one way of kind of asking this question in a more general way. So right now I just showed you a single example. But if I wanted to ask this question of partial redundancy elimination in a more general way, I want to ask the question, can we place computations of b plus c such that no path recomputes the same expression? All right. So basically no program path. So recall that there could be potentially an infinite number of program paths in the program because there are loops and other things. But can we place computations of any computation? So in this example, I'm using b plus c as an example, or any given computation such that no path recomputes the same expression more than once, right? So if on that path it has already been computed and it has not been killed. For example, if I'm computing b plus c, then b hasn't been set to 7 or something like that, or no other value, or c hasn't been set to some other value, something like that. So as long as that expression is available on that path, I'm not going to recompute that expression on that path. All right. So this is very similar to the available expressions analysis that we've seen earlier, just that in the available expressions we had the mandate that it should be available on all paths. Here we are saying that, and we would say that there should not be redundancy if it is available on all paths. Here we are saying that look at each path in isolation, and even on every single path there should not be any redundancy. So that's a much more difficult statement or analysis to kind of imagine. So first of all, I want to point out that partial redundancy elimination subsumes loop invariant code motion, and that's easy to see because if I have a loop and let's say this m plus n is a loop invariant computation, then m plus n is redundant on many paths. For example, if I just take the path which goes around the loop once and then goes out, here m plus n is being redundantly computed once more, right? So in total it's being computed twice, but redundantly computed once, right? So once it's the first time you need it, but the second time it was redundantly computed. Or even if I take a path which goes around the loop 3 times or 10 times, then m plus n is being redundantly computed, twice or 9 times or things like that. So here there is partial redundancy, right? So involves redundant computation on loop paths. So there are some paths where there is redundancy, and so this expression, this program has partial redundancy in it. What would be a way to solve this problem? Well, one way to solve this problem is to basically eliminate the partial redundancy by doing loop invariant code motion. You recompute m plus n ahead of the loop, and then you just do a equals t inside the loop, and now I have eliminated partial redundancy on this particular program, because in this program m plus n is computed only once on all the program paths, right? Irrespective of whether, so let's take a program path that goes around the loop 10 times, even there m plus n is only computed once. All right. So partial redundancy elimination, or PRE, subsumes loop invariant code motion, or LICM. All right. Now, here is an example that shows that PRE may require adding basic blocks. So here is an example. So for example, you have C equals A plus B, and then from somewhere above in the program there is another basic block, and there is some computation here, and then there is a meet point where I say D equals A plus B. So now once again A plus B is being partially computed on some of the program paths. For example, on this particular program path A plus B is being partially computed, but if I look at this particular program path, A plus B is not partially is not redundant. So here it is redundant on this particular program path, it's redundant. On this program path it is not redundant. So A plus B is redundant on some paths. There is partial redundancy with respect to A plus B. The question is, how should I remove this partial redundancy? Now notice that if I bring this A plus B here, so if I bring this A plus B here, then that's not a good idea, because then I have introduced redundancy. So I have eliminated redundancy on this path. So with this, if I bring A plus B here, let's say, so let me just draw an arrow. So let's say I bring this here, then I have eliminated redundancy on this path, but I have introduced a redundancy on this path, because on this path A plus B was not getting computed, probably it was not even required, and still I have put A plus B computation there. So one of the other things about redundancy is that only those expressions should be computed which are actually required on that particular program path, right? And so here, I mean, in the original, so I shouldn't introduce any extra computations on any of the program paths in the program. But if I move a plus b here, then I have added an extra computation of a plus b on this particular program path. And that is not an acceptable solution for partial redundancy elimination, because to eliminate redundancy on one of the paths, we are kind of adding redundancy on another path. We are adding extra computations on another path where they were not even required. All right, so that is not something that we would like to have in our solution, and so it is not okay to compute a plus b here. All right, so this is a bad solution. So what is a better solution? Well, first of all, I want to point out that why is this problem even occurring? This problem is occurring because there is an edge here which basically has a basic block which has two successors, and so the from basic block of this particular edge has two successors, and the to basic block of this particular edge has two predecessors. And so if I want to move a plus b into this here, then I'm adding extra redundancy on some of the program paths. For example, I'm adding redundancy on this particular program path. So what is the solution? The solution is to add a new basic block which basically breaks this particular edge into two edges. All right, so and that way I'm being able to remove redundancy on this particular path without adding redundancy on this particular path. So on this particular path, a plus b is not getting computed. On this particular path, a plus b is only getting computed once, and on this particular path, it is also getting computed before it is getting used. So it's all good in this situation. So in this case, we had to eliminate the partial redundancy. We had to add an extra basic block. And why did we have to add an extra basic block? Because I wanted to break this particular edge into two edges so that I can place a computation in the middle of that edge. I didn't want to place the computation at the source of that edge. I wanted to place the computation in the middle of the edge. So what is special about this edge that I had to break it into two and place a computation in the middle of it? Well, it's because this edge is so special because as I just said before, its from node has two successors and its to node has two predecessors. And that's why it becomes difficult to move a computation or hoist a computation. When we move a computation above, earlier in the program, then we call it hoisting of a computation. So it becomes hard to hoist a computation because across a critical edge, because now you may be adding redundancy on some other parts of the program. And so I need to break the critical edge into two edges and insert a basic block in the middle of them. So what is a critical edge? A critical edge is an edge where the source basic block has multiple successors and the destination basic block has multiple predecessors. So here is an example of a critical basic edge. This particular basic block has two successors and this particular basic block has two predecessors, two or more predecessors, two or more successors. All right. Critical edges make it harder to remove redundancy because if I have a plus b here and let's say a plus b was also being computed on some other path in the at some of the predecessors of the destination node of the critical edge, then I don't know where to put a plus b, because if I put it here, then I'm adding redundancy on this particular path and that's not a good idea. So where to hoist a plus b if it is redundant on the other incoming edge of the destination? Well, the answer is that you need to add a new basic block for that particular critical edge. So this is going to be a feature of our algorithm. We are going to we may have to break critical edges into two edges and put a basic block in the middle of them to be able to eliminate partial redundancy. Now, I want to point out that partial redundancy may still not be eliminatable even after adding basic blocks. And here is an example. Here basically I have A equals B plus C and D equals B plus C, and I have this diamond shaped two diamonds. I have a program structure which is made of two diamond shapes. There is a meet point first, and then again there is branch, and then there is meet. And now it is B plus C is computed on one of the branches in the first diamond, and then it is recomputed on one of the branches in the other diamond. Now, in this particular example, if you look at this particular path that has been marked in green, then the expression b plus c is computed redundantly twice in this particular path. On the other hand, if I look at any other path, there are 4 paths in total in this other program, and on the other 4 paths there is no problem of redundancy, but on one of these paths there is a problem of redundancy. The question is how to remove this redundancy, and the thing is that here it's not enough to just add a basic block to remove this partial redundancy. In fact, here if you want to do this, you may have to duplicate the code by duplicating this part of the second diamond of the program, right? So this program is made up of 2 diamonds. The first diamond structure involves branching and then meeting, and the second diamond structure again involves branching and meeting. And one way to eliminate partial redundancy in this particular program is to copy the code of the second diamond for each branch separately. So specialize the code for each branch, and then in one of the branches eliminate the redundancy, and on the other branch there is no redundancy anyway, and so that way we can achieve partial redundancy elimination. So to see that, what I can do is, in this particular example, I have first kind of eliminated this B2 to specialize the code of the second diamond on the left hand side path, and so this is what I get. And on this particular path I've already computed b plus c, so I can reuse that, and so instead of recomputing b plus c, I can just say d equals t, where b plus c is already computed into t. And for the other branch, I copy the original code as it is. Now you can imagine that when I copy the code, then the code size increases, and that can also have a dramatic effect on the runtime because of caching effects and things like that. Moreover, when we duplicate code like this example, then what happens is that the code size increases by a multiplicative factor, and when there is a multiplicative factor involved, things can quickly become exponential, right? So if you start duplicating code like this, then the program can really become really big, and that can be detrimental to performance. And so, but nonetheless, even if I'm doing that, I can be a little smart about this. So maybe I just duplicate B3, but then from B3 the outgoing edges are kind of shared. So for example, if B3 goes to B4, then both B3 and B3 prime, which is the copy of B3, can go to the same B4, right? Whereas for D equals B plus C, one of them has a specialized version, D equals T, and the other one has the original version, which is D equals B plus C, and both of them can now go to B5. And so this would be our transform program. Notice that in the transform program, I have duplicated B3 and B3 prime. And so to be able to remove partial redundancy, I had to duplicate. You can check that in this particular program, once again, there are 4 possible paths, and on all those 4 paths, there is no redundancy. So we have successfully implemented partial redundancy elimination, but unfortunately, we had to duplicate code to do this. We are not interested in our particular algorithm. We are not interested in duplicating code because, as I said, duplication can quickly become exponential in nature and can have detrimental effects both to code size and to performance. And in our work, we are interested in eliminating only those redundancies which can be eliminated without code duplication. All right? We are not interested in code duplication, but without changing the control flow graph structure by much. There are some things that we will still allow, and that is the addition of basic blocks is still allowed on critical edges. But apart from that, we don't want to modify the control flow graph structure in any other way. Yet we want to eliminate partial redundancy wherever possible in such a restricted setting. So that's what we're going to be discussing in the next few lecture modules.